You board a jet on the West Coast before sunrise. You land in Tokyo before the workday ends. The math seems wrong. At Mach 5, it is not. This is the arithmetic of a new era, one that stopped being theoretical the moment a specific aircraft cleared the runway at a high desert airbase, and the telemetry confirmed what the engineers had calculated but barely dared to believe. The mission is dual. Sanitize enemy radar networks before a strike package arrives, and compress the transoceanic commute into minutes, not hours. For the better part of a decade, both objectives were considered physically unreachable. The reasons were well understood. The solutions were not. What changed was not the physics. What changed was who decided to fight them. For most of the decade, from 2010 to 2019, the Pentagon faced a problem no budget could solve. Russia fielded the Zircon missile at Mach 8 and the Avangard glide vehicle at Mach 20. China deployed the DF-17 with a hypersonic glide vehicle designed to defeat carrier strike group defenses in the Western Pacific. Both shared one critical trait: non-ballistic trajectories. They maneuvered the Aegis combat system and THAAD against a Mach 5 glide vehicle executing lateral maneuvers at 100,000 feet were effectively spectators. Washington's answer was the Air-Launched Rapid Response Weapon, ARRW. It accumulated delays, failed a string of tests from 2021 to 2023, and was canceled in 2023. The gap had a new data point. What the military needed was specific, not another ballistic re-entry vehicle. An ICBM warhead crosses hypersonic thresholds briefly, then impacts. A Crew Dragon capsule endures peak heating for minutes, then deploys parachutes. Neither sustains hypersonic velocity inside the atmosphere for a mission. Neither reconnoiters, loiters, and returns to base. That is a fundamentally different problem. A vehicle designed to suppress radar networks and withdraw before intercept must fly at Mach 5 continuously, within the atmosphere, for the duration of its mission. Recoverable, reusable, taking off from a standard runway without a booster or airborne launch platform. No existing US program was on a credible path to deliver that. The gap between simulation and hardware had become, by the early 2020s, a credibility crisis. The answer was not coming from the programs that had already failed. That team was already working. On July 28, 1976, SR-71 pilot Eldon Joers set the record for absolute airspeed at 2,193.2 miles per hour, Mach 3.3 over the Mojave Desert. That record has not been broken in 50 years. Lockheed Skunk Works built it from titanium, 93% of the structure, with slide rules and pencils. The SR-71 was targeted by more than 4,000 surface-to-air missiles. It was never hit. But Mach 3.3 is not Mach 5. The gap is not arithmetic. It is thermodynamic. The J-58 engine's inlet geometry could not manage compression heating beyond Mach 3.3 without destroying itself. The Blackbird was not held back by ambition. It was held back by the physics of its own operating environment. Concorde met the same wall from a different angle. Mach 2.04, approximately 1,176 knots, was the fastest commercial aircraft ever to enter passenger service. New York to London in under 3 hours, an achievement unmatched since its final flight in October 2003. But above Mach 2.2, intake air temperatures destroy turbine compressor blades. Concorde was trapped by the thermodynamic limits of turbine architecture. Between those two ceilings, the sustained hypersonic atmospheric vehicle remained an engineering target with no credible solution. At Mach 5, the nose cone endures temperatures approaching 3,000 degrees Fahrenheit continuously. Aluminum would not survive the first minute. It would behave like candle wax over an open flame. Even titanium deforms above 800 degrees Fahrenheit under sustained load. The thermal barrier was a materials science problem the industry had been working on without a definitive solution for 50 years. The barrier was known. The team willing to fight it had not yet arrived. Power vacuums never last long. The company was Hermeus, founded by alumni of SpaceX and Blue Origin. The philosophy was simple: build real hardware, test it to destruction, extract the data, and rebuild immediately. Traditional contractors spend years on white papers before committing metal. Hermeus inverted that sequence entirely. The program, Quarterhorse. The mission was to develop a hypersonic unmanned aerial vehicle to surpass the record of the SR-71 and to field a platform serving both defense and commercial markets. CEO A.J. Piplica brought propulsion experience from SpaceX. The team drew from Blue Origin and the Air Force Research Laboratory. Fewer decision layers, faster iteration cycles, hardware on the test stand in months, not years. This was not iteration. This was replacement. But ambition at Mach 5 lives or dies on one thing, the engine. And what Hermeus built had never been flown before. The engine is called Chimera. It is not one engine, it is three, forced to operate as one. No single propulsion technology covers the full speed range of a Mach 5 mission from a conventional runway. A turbojet excels at takeoff but destroys its compressor blades above Mach 3. A ramjet dominates above Mach 3 but produces no useful thrust at low speeds. A scramjet owns Mach 5 or higher but is useless below it. Each technology owns a portion of the flight envelope. None owns the whole thing. Chimera forces them to share it. The architecture is a turbine-based combined cycle engine, TBCC. Approaching Mach 3, the system must divert airflow away from the turbine compressor and into the ramjet combustor, while moving at 2,000 miles per hour. Imagine removing a car's gearbox entirely while continuing to accelerate. The swap must happen seamlessly, or all propulsion is lost. That is the TBCC transition problem. Hermeus calls the critical moment the aerodynamic valley of death. If the turbojet shuts down too early, the aircraft loses thrust at Mach 3 in the upper atmosphere. Not recoverable. If the ramjet ignites too late, the unstart, a violent airflow choke, tears the airframe apart. The vehicle does not glide, it comes apart. In November 2022, at the Notre Dame Turbo Machinery Laboratory simulating Mach 4 conditions, Hermeus confirmed successful mode transition without an unstart. The door had not been opened. It had been kicked off its hinges. Proving the transition in a laboratory was one milestone. Surviving Mach 5 continuously required solving thermal management at the engine intake. At Mach 3+, intake air reaches 800 degrees Fahrenheit before combustion begins. Without intervention, titanium turbine blades soften within seconds. Hermeus selected the Pratt and Whitney F100, the engine behind the F-15 Eagle and F-16 Fighting Falcon, with more than 30 million combat flight hours in U.S. Air Force service, as the Chimera II core. That solution is the pre-cooler, a miracle radiator at the front of the engine. It drops superheated intake air to a safe operating range in a fraction of a second. Built from a micro-channel heat exchanger using Inconel 718 and metal 3D printing. The F100, managed by the pre-cooler, can now be pushed beyond its original certified envelope to reach the velocities where the ramjet takes over. For the airframe, titanium aluminide heat shields protect the nose cone and wing leading edges, while ceramic matrix composites, CMCs, cover broader surfaces. CMCs offer thermal tolerance 3 times greater than titanium at 1/3 the weight. In January 2025, Hermeus activated a heat test facility in Jacksonville, Florida, the only private facility on U.S. soil capable of replicating sustained hypersonic conditions on the ground. The components were proven. What remained was the sky. Early 2024 marked the moment the program stopped being a promise. Mark 0, the Iron Bird, never left the ground. Over 37 days at the Arnold Engineering Development Complex in Tennessee, it validated software, command and control architecture, radio frequency latency, and runway taxi capability. It was designed and assembled in 6 months. 1 month later, Mark 1 was announced. 1 prototype per year. The date was May 27, 2025. At Edwards Air Force Base, where Yeager broke the sound barrier in 1947, where every American experimental aviation milestone has been written into the tarmac, Quarterhorse Mark 1 lifted off under full remote pilot control. It executed stability maneuvers, demonstrated its double delta wing configuration, and landed safely. Telemetry confirmed lift and drag prediction models at less than 2% margin of error. White papers do not generate Air Force contracts. Flying prototypes do. By late 2025, Mark II, integrated with the F-100 and Chimera II, had been transported to Spaceport America, New Mexico. The 12,000-foot desert runway surrounded by restricted airspace was selected for a reason. What Mach II was about to attempt could not be done at a civilian airport. The final objective is Mach 5. Everything before it is preparation. Mach II will shatter the sound barrier under Chimera II power, sustaining supersonic flight approaching Mach 2.5. If it succeeds in early 2026, it unlocks ramjet mode activation, and that moment belongs to Mach III. Mach III, targeting late 2026, will execute the first live Chimera mode transition in actual flight. The turbine will shut down, the inlets will reconfigure, and the ramjet will ignite. Hermeus calls this the bridge, connecting 20th century aviation to the 21st century. If it succeeds, Mach III will surpass 2,193.2 miles per hour and end the SR-71's 50-year record, triggering Defense Innovation Unit contracts and full Air Force backing for Darkhorse. The competition is real. Stratolaunch confirmed Mach 5 with Talon ATA-2 in March 2025. Lockheed's SR-72 is reportedly testing in Nevada. Project Mayhem is advancing toward restart. Each program carries a constraint Quarterhorse does not. Stratolaunch needs its rock mothership. The SR-72 operates on a classified timeline. Project Mayhem is expendable. Quarterhorse takes off from a standard runway, flies the mission, and lands for turnaround. No mothership, no booster, no single-use airframe. This is precisely what military doctrine requires. It is precisely what no program before Hermeus has delivered. Every revolution in aviation arrives in two waves. The first belongs to the military. The jet engine flew combat missions before it carried passengers. The SR-71 cruised over denied airspace for 2 decades before anyone discussed its implications for civilian travel. Quarterhorse follows the same arc. Darkhorse will operate outside the engagement envelope of Russian S-400 and S-500 systems, launching from Guam, reaching the South China Sea in under 30 minutes, suppressing radar networks and withdrawing before intercept. The B-21 Raider follows into the cleared corridor. On the commercial side, Hermeus's Halcyon program targets New York to London in 90 minutes at business class fares. The regulatory path, including sonic boom certification through NASA's Quest program and G-force management, is measured in years, not months. The aircraft exists. The propulsion system has been ground validated. The first flight is on record. What do you think happens first? Does Darkhorse enter operational service before a commercial hypersonic jet carries its first fare-paying traveler, or will the civilian market move faster than the Pentagon allows? Leave your thoughts below. Subscribe and hit the notification bell. The next milestone is weeks away.